All right, welcome. Here we are. We're in lesson 1. This is lecture 1. And we're going to deal with Python data types and data structures. So at this point, you should have already reviewed the course syllabus, the course contract, completed that, and reviewed the course structure itself. By completing the course contract, you should have met your attendance verification requirements, and just make sure that everything you need to have done up to this point you have done, and that you have a good understanding of how the course is laid out, how to navigate Canvas. If you don't, reach out to your faculty and get whatever needed clarity may exist. So we've got certain expectations of your current abilities and your understanding when it comes to programming. We have an expectation that you can write functional code. You understand the concepts of code organization and structure, documenting your code, how the logic and flow charting and pseudocode work, what object-oriented programming is, and should there be any deficiencies there, something you don't feel strong in, please reach out to your faculty member or the SLC to remediate any deficiencies that may exist. It's best now to strengthen up any shortcomings before we move forward. Some of the concepts that we're going to cover can be very intimidating if you're not feeling strong coming into this course. Okay? So we're going to deal with a variety of resources in this course. We may use some GitHub resources. We're going to use Google Colab, and you'll see some more of that in this lecture. It won't be next lesson, but I do want you to go through and get your Google Colab account set up and become familiar with that. Right. So we're going to be doing some programming. And at this point, you should know how to program. You should be familiar with data types. Now, we're going to use the Python programming language for a variety of reasons. It's simple. It's lightweight. It's the most widely taught programming language today. In this programming language, we have data types that we use, numeric, Boolean, sequences, and then there's some complex data types that we'll use. Numeric, we use an integer, a float, which is a floating decimal point, and then we can use complex numeric data types. Boolean is just a simple yes or no, true or false. And then we've got sequences of data, which are data types, be it a string, a range, a tuple, some may call it a tuple. And then we've got a list. Now, if you've used up to this point another language, not all languages use the same data types. So let's step up a level and look at this from, let's say, a 10,000 foot view. There's a library built into Python. It's a standard library. And in that library, we think of a library, we think of books. In that library are classes of code. They're like books, in a sense. You go into a library to check things out. Well, I go into my standard built-in library to utilize resources that already exist, these classes of code. There's an integer class, there's a float class, there's a complex data type class, there's a Boolean class, string class, range, tuple, list. Each one of those classes has everything we need to be able to create an instance of an integer. I want to store something and I want to treat it like an integer. But for me to be able to store that data, I need to know the rules associated with it. So that's where these built-in libraries come from. Now, we've also got other libraries that we'll talk about here in a little bit, but at this point, we've got these data types. And we understand these are numbers. This is that true or false. These are sequences of a variety of things. So, a string, it's a sequence of characters. A range, it's a sequence of something that goes from one position to the last position. So a starting point and an ending point, and then there's the stuff in between. And we commonly see something like this when we're talking about, let's say, a for loop. For something in this range from 0 to n, and I don't know what n is, and everything in between 0 and n. That's a range. So somebody's built a class associated with range, and it has functionality and attributes associated with it, and we can use it. The big two that we have are tuple and a list. They're very similar. The only significant difference between the two, and it is very significant, is a tuple's immutable, meaning what you put in it does not change. We define it, it stays the same. Now, conceptually, it's similar to a constant, but we don't call it a constant, we call it immutable. A list, we could change it at any point, change what's in there. A list is a sequence of things that we're storing. Now, the sequence, when we look at strings, that's characters. A list can have a sequence of any other data type that we have to play with. It could be a list of integers, floats, complex. It could be a list of strings. It could be a list of tuples. It could be a list of complex data types like dictionaries or sets. And on top of that, we're not limited to just one data type. So it could be a list that contains some dictionaries, some floats, some strings. It can get real messy when we're trying to work with it, perform some tasks associated with what's in there. But that's what a list is. It can hold just about anything that we've got to throw in it. Now, that could be a good thing and it could be a bad thing depending on how we look at it. When we talk about complex data types, we've got a dictionary, and a dictionary can hold two things. We've got our value, and then we've got a label. When we think about a dictionary, we think about like a word and a definition. A single word can have multiple definitions. Okay. We've got a label, and it can have multiple values. There we go, dictionary. Sets are different. Right. Sets of values. Right. And we'll deal with these as we move forward, the different data types and the ins and outs of them. Now, one of the things when we're talking about Python, I said Python was really light and efficient. It's also dynamic in that we can add on additional libraries. Now, we've got this standard built-in library. And let me bring this on over. Here's our standard built-in library. And I'll share this presentation with you so you can click on that link that I just clicked on. But we've got all these built-in types, sequence types. There they are. Numeric types. Oh, there they are. So if you want to dig in to see the different things that exist, we can go dig into the standard Python package. What comes in our built-in library. So when you install, which you don't have to do for this course, you don't have to install Python on your machine. We're going to use Google Colab to be able to do what we have to do. That way you can do what you have to do on a Mac, you can do it on Windows, you can do it on whatever. We're outsourcing the libraries, if you will. So I can utilize the standard library, or I can add in other libraries like NumPy or PyTorch. Here's NumPy, and NumPy allows us to create n-dimensional arrays. So, well, wait a minute. An array is a data type. An array is different than a list, because a list you can have whatever you want in there. An array it's a sequential structure, sequential data type, but it's all of the same data type within it. So it's an array of integers, or it's an array of floats. They're all the same data type within this sequential structure. So why do we need NumPy? Well, I said that Python was really lightweight. It's so lightweight that it didn't include a array class. So we had to have an extra library to be able to get that. And there's other classes like random number generator, things like that. And there's other libraries that we can add in. PyTorch. If I want to go through and maybe do some machine learning or something along those lines. TensorFlow, another one. If I wanted to do machine learning or maybe some deep learning. Scikit-learn. And there's so much we can do there with data visualization, data analytics. Now, some of these things are tied to other libraries. So the libraries kind of rely on one another. So just know that we're using Python, just like any other language, programming language. It's founded on some library of code. We have the ability to point to additional libraries as needed. Now, these libraries contain classes of code. It's an int class, it's a float class, and I can instantiate that class and create an instance of that class. So I've created an integer object or a float object. I can reuse it all I want. I've reserved space in memory for a float object. And when I reserve that space in memory to be able to do what I want to do, I followed all the rules associated with that float class. And I inherited all the functionality and attributes of a float. So in object-oriented programming, it's something you need to be familiar with coming into this class. It's founded on 4 key principles. Encapsulation, which is grouping related data and functions together. Inheritance, deriving new classes from existing ones, or creating objects. So I can have a parent class and derive a child class from that parent class, and inherits everything from the parent, and I can add more onto it. Now this is creating an additional class that I can create objects of. We've got polymorphism. It's a single interface, multiple implementations. And we've got abstraction, which means we've got the ability to hide complexity and display only certain things. So there's functionality behind the scenes that I don't need to know how it works, or I may be dangerous if I'm allowed to interact with it. So abstraction is a layer where we can hide things from the user or from the code, so that it makes sure that, in many cases, what it does is it makes sure that this object that we're creating is reliable. Bad things won't happen to it accidentally, or could be something somebody did maliciously. So, like I said, we're going to deal with Jupyter notebooks. And here's one that I've created just for this lecture. So we see it's in Colab. It's got my account. I can go in and I can share it, give anyone access to it. If I don't do this, people can't access it. And then I copy that link and it's shareable. But I have to make this link shareable. Right. So I've made that link shareable and I've embedded it in this presentation. And then anybody can access this notebook, make a copy of it, and go do whatever they want to with it. So we've created, I've got a text box here. Here I've added text. I've created some code, a block of code. And in this block of code, I don't have a bunch of comments in this because it's just copied right out of the text. This is something that happened in the textbook in that first chapter. They declared a instance of the dictionary class called myDict. Now, we don't have to be explicit when declaring this as a dictionary, but the fact that we put these curly braces on here, curly braces in Python, represent a dictionary. If I was in C# or something else, these curly braces mean something else. So syntax is a big deal, and we'll get familiar in the first chapter and any supplemental with the syntax of Python. So I've created a dictionary, and we've got the label and value, label, value, label, and value. So the analogy, or when I compared it to an actual dictionary, word definition, and I can have multiple definitions in there. Word, well, we only gave it one, could give it more than one. And then I say I want to print off my dictionary, and I just click this, it'll execute the code, and it says here's your dictionary. I cleared the dictionary, meaning get rid of all the values that are in it, and then I printed it again. So this makes it easier for us to go do what we want to do. We can go create our own notebooks, go create it, give it a name, whatever I want to do, and just start writing code to do whatever it is I want to do. Much of what we're going to do is going to be conceptual and theoretical, but at the same time, we need to be able to have hands-on and perform the coding aspect of it. So I've created an instance of a dictionary. The dictionary class is built in, and by using these curly braces, it knew I wanted to create an instance of a dictionary class. So I've got this object, myDict, or we'll call it a variable. And that's my dictionary. And so we created an instance of it, kind of cloned it in a way. And now it's, call it an object. This is where that object-oriented programming comes from. So I can use a built-in function which is a dict function, which essentially says, all right, what's in there? What this dictionary class that you used, where you created an instance of it, what'd you have to play with? What is it that you cloned? And I just wrote a little statement here using the print function, and I passed it a directory function for, I think I've got a typo there. This shouldn't be dict, this should be directory. There we go. I wanted the directory function, and I passed it my dict, which is that object we created. I say, hey, here's this object. Show me the directory of all of the attributes and everything. So this directory function will go through and tell me everything that's in there. There's a len function in there. It'll tell me how long this thing is. Go see different attributes, the size of it, string, clear, copy, all of the functionality that got inherited. Pop item, set default, update, get. So all these things that exist within the dictionary class, I just inherited them in my dict. So I could create an object this way, or here's another way to look at it, is I want to create my own class, and I'm going to call it number. My class has attributes associated with it. I create a constructor that will initialize an instance of this class, and here's the work that happens in it. And that's my class. I say, you know what? I'm going to create an instance of it called n. This will invoke that constructor, the init function, and it passes it this argument, or the attribute of 2. So when this constructor fires off, it says, hey, is anything being passed to you? Yeah, the number 2. All right, take that number 2 and put it in this storage facility that we've created. And when we need it, we got it there to use. So let's go ahead and show what we've got. Oh, we've predefined those 3 attributes. What are they? They're strings, aren't they? Three different strings. So self.1 has first in it. Self.2 has second in it. Self.3 has third in it. And then we said, let's go ahead and print out whatever's in that attribute that got passed in right here. So when I said n.show, it invoked this method or this function right here, told it to run. So we see that here. First, second, third, that's what's in there. And then that last attribute that got passed to it. Now the directory function that we talked about above, let's see what's in n. All right, right there. That's everything that's in n. All right. What's in number? The parent. N is the child. Numbers. The parent. Look at there. Now, what do we see different? Attribute. That's the only thing different. So When we go through and do this object-oriented programming instantiation, I created a clone of number, but then I said, you know what? I want to personalize it. I want to make it unique. It's also going to get something extra. So in this instance, the child got something a little bit extra, which is that attribute that we passed to it. It's object-oriented programming. So this is something we're going to use over and over again in what we're doing. We're going to utilize certain data types, create instances of them applying specific rules so that we can perform tasks in a specific way. We got to do things a certain way in this. So at this point, you can create solutions that are functional. You can program. Somebody said, hey, go ahead and write a program that says hello world. That's easy. My goal is write a program that outputs hello world. I can do that. I can create a solution that's understandable. You can create, should be able to at this point, that creates a solution, computer programming code, that is understandable. Somebody else can come behind you and look at your code and understand what you're doing. You've put comments in there to explain what you're doing and how. You have white space, that area between that shows us the organization of what we're doing. But can you create solutions that are efficient? Can you create solutions that are scalable? Ones that are effective? These three things is what we're going to deal with now, moving forward. Hello world, one blanket statement. What if you actually had to say hello to every individual in the world? That's scalability. Now I'm not just doing it once. I'm doing it billions of times. Is it going to be the same code to do it? Will it work? How long will it take to run? What we're doing now and moving forward is looking at how the code we write interacts with the resources we have available. Oh, wait a minute. Resources available. We're going to go through and we're going to look at algorithm design. How we structure what's taking place. The techniques and strategies. We're going to look at linked lists. These are data structures. So data structures are different from data types. Data types, we'll look at them as the class that we're going to use. We're going to create instances of those classes with specific rules in mind to create a data structure. Some classes may work to perform an effective and efficient structure, others may not. Now, go back. I said efficient. I said effective. Aren't they the same? No, they're not really. When we're talking about efficient, think about that hello world. Well, I can write code that says hello world. It says hello to everybody at once. Can they understand it? No. Because they all aren't speaking the exact same language. Not everybody understands the same language. Oh, so now we need to write code that does it in every language. Well, if you want to be effective, yeah. How long is it going to take? Ooh. I remember one time a few years ago, I was ambitious and I was taking a graduate algorithms and analysis and design class. And the professor said, I want you to go perform this task. And you choose whatever algorithm you want. I said, okay, I'm going to use this one. Sure about that? Yeah, I like that algorithm. I like the concepts behind it. Okay. It took me a couple of weeks to realize that that algorithm was functional. That algorithm was clearly understandable. That algorithm was scalable. I could do it with a data set of n equals 10 or n equals 10 billion. Didn't matter. It'd still function. It wouldn't break. Was it efficient? Well, long and short of it, with the resources I had available to me, the computer that I have, it would have taken 164 years for that program to run. Now, that's not very efficient. Could it have obtained my goals? Been effective? Yeah, but I want it to happen in my lifetime. I really wanted it to happen this week. So that's where the efficiency part comes in. We're limited by constraints when it comes to the systems we're dealing with. The computer you have can only work so fast. The computer you have only has so much RAM. The variables, the data that we're bringing in to manipulate, goes into RAM when the program's running. Massive amounts of data that we're going to use will require massive amounts of RAM depending on the algorithm. If I don't have enough RAM, it slows down. If I don't have sufficient processing capacity, it's not necessarily going to stop, but it may time out. The system may just say, look, I'm done trying. Or if I've got it set up to where it's going to keep trying until we're done, it's going to be running for that 164 years until it finally says, here's your solution. So I started this slide out with, we can do better. We can do better by utilizing more efficient algorithms. Doing things in a different way can get the same job done using fewer resources, be it time, RAM, processing power. We want to minimize those resources used. We want to be efficient, and we still want to be effective. We want our solutions to be scalable. That's what, in a nutshell, this course is going to be about. So when we move into this next module, which is Introduction to Algorithm Design, we're going to start looking at the algorithms, how they work, and we're going to look at concepts that are time and space complexity. In a nutshell, what that means is, all right, we're going to look at an algorithm, and if I choose this one, is it going to require a lot of processing power? Am I going to need multiple core processors, multiple processors? Am I going to need to have access to GPUs to do whatever it is to get it done in a realistic amount of time? Am I going to need massive amounts of RAM, which is our space complexity? And then from there, we'll get on to the next chapter, which will deal with algorithm design techniques and strategies. Then we'll get into and look at the different structures and how one structure is better than another, when to use one over the other, strengths and weaknesses of each of these data structures. Okay. So from that, I'll see you in the next module, which will be Introduction to Algorithm Design, and we'll deal with Big O notation. And see you there.